All right, in this video I'm going to talk about manipulating K and how that works in terms of if you're given multiple reactions with multiple K values, what do you need to do? The short version of this is that this topic is extremely similar and related to the idea of Hess's law, which states that if basically any change that you do to a reaction, meaning flipping it or changing the coefficients in any way, it has to be mirrored in the change to the enthalpy value. So we've seen that before, that idea of Hess's law. Well, this is now tying that in with K values and equilibrium constants. So just as if you flip a reaction, you have to change the sign on delta H, you have to manipulate K. That's what I mean when I say manipulating K. But the thing is that it doesn't work. The manipulations don't work the same way. You cannot have a negative value for K. You can't, because K is a comment on the relationship between the concentrations of the reactants and the concentrations of the products. You can't have this any sort of negative relationship, so you can't reverse the reaction and then flip the sign on K. There is no sign on K. It's always positive. It's just what's the relationship between products and reactants? It's a fraction. It's a numerator and a denominator. So instead of taking the negative of K, which you cannot do, it makes no sense, if you flip a reaction, now you're going to take the inverse of K, take the reciprocal. You're going to flip that reaction around, because if you write out a reaction where what used to be your products are now your reactants, well, think about it. K is products over reactants raised to their coefficients. You just changed what are the products and what are the reactants. Ergo, you are going to take the reciprocal value for K. So if you flip a reaction around, you need to take the reciprocal value for K. Additionally, if you multiply the coefficients by something, instead of multiplying the delta H value by that same thing, now you're going to simply raise K to that power, because K expressions are products over reactants raised to their coefficients. You change the coefficient, you changed the power, not a multiple. You're not going to multiply K by something, you're going to raise K to that power. Right? You make the coefficient 2 instead of 1. That will be reflected by having the exponent be 2 rather than the exponent be 1. And then finally, if you add reactions together, like in Hess's law, you add the reactions together at the end in order to get the target reaction, instead of adding the K values together, which is not appropriate, now you're going to multiply the K values together. And so it's slightly different rules that take into account that K as an expression is products over reactants raised to their coefficient. So the rules are reflective of that. So what I'm going to do now is go through a really quick sample problem. It's actually not in your notes. Let's see. The one that I made up that doesn't have actual reactants, but it's basically a Hess's law to see how we can use what we already know about Hess's law and fit that in with what we know about manipulating K. So take, for example, we have A plus B goes to 2C, and this is K1, whatever that value is. And then we have C plus E goes to F plus G, and this is K2. And we have B plus H goes to 2F, and this is K3. And it's asking, it says, a question might be, what is the K value for the target reaction A plus 2E goes to H plus 2G? We solve this just the exact same way that we solve a Hess's law problem, meaning the first thing that you want to do is look at the target reaction and think about what changes you need to do to the reactions that you're given in order to get what you need. So if I look at this, we want this, and if I look at this very first reaction, A plus B goes to 2C, I look at, remember the key to Hess's law is about looking for things that you need in the target reaction that are in the reaction that you're currently looking at. So when I see this, and when I see this target reaction, I notice that I have A, and you look at its location, you look at how many of it you have, and in this case, I need 1A in my target reaction, just one, and I need it to be on the reactant side. Well, this reaction, as written, already has A, just one of them, on the reactant side. So I'm going to keep this reaction as it is. So this is, I'm just going to keep it. A plus B. I'm going to rewrite it because I'm going to do all my canceling on this side. Next up, C plus E goes to F plus G. So I evaluate each of these reactions for what I need. When I look at the target reaction, you're looking for things that you have in this equation that will help you get to what you want. So I noticed that, okay, this thing has E, and this thing has G, and this thing has E, and this thing has G. But I need 2 of the E's and 2 of the G's. Now they're in the location, so I don't need to flip the reaction around, but I do need to multiply this reaction by 2. So this is going to turn into 2C plus 2E goes to 2F plus 2G. I'm going to deal with the K's afterwards. And then last up, B plus H goes to 2F, the last one. What do I need there? The thing that I need there is the H. I need one H, and I need it on the product side. But in the reaction that's written in the B plus H goes to 2F, the H isn't on the product side. So I need to flip this reaction around to get it on the product side. So I'm going to flip this around, and I'm just going to rewrite it over here. 2F goes to B plus H. Now I'm going to add these reactions together to ensure that I do in fact get the target reaction from them, and then I'll talk about what we're doing to the K. So just ensuring that everything cancels. Let's see, anything that's the same on both sides will go away. So the 2 C's, those go away. 2 F's, that goes away. And I also have a B here and a B there, so that will cancel. If I add these together, I get A plus 2E goes to H plus 2G, which is exactly what I want. So I know that I've manipulated the reactions correctly. But now let's take these manipulations right here and this, because that's a manipulation as well, and apply them to the K value. So this one, the very first one, A plus B goes to 2C, we didn't do anything, so I'm going to keep that as K1. Right, that value is going to stay the same. I'm going to erase some of this so we have a little bit more room to work. This was K2, the second one. Now, we doubled this. I'm not going to double K2. I'm going to square K2. If you double a reaction in terms of coefficients, you need to square the K value because you have altered the coefficients, and coefficients are powers when it comes to K. Next up, K3. We flipped this reaction right here. So I'm going to take the reciprocal of that for K3. So now, instead of K1, K2, and K3, now I have K1, K2 squared, and 1 over K3. We added these reactions together. So for K values, what we're going to do is multiply all these values together. So the K value for this reaction, based on these manipulations that we did, is going to be simply the product of K1 times K2 squared divided by K3, because we took the reciprocal of it. So you multiply your K values when you add the reactions together. And I didn't put in actual numbers, this is just to show you the idea behind it, but that's how you would work with, basically how you bring in the idea of Hess's law, but with equilibrium constants rather than enthalpy values. Same idea in terms of manipulations for the reactions, but the manipulations are represented differently when it comes down to how the manipulation affects the value for K. You cannot simply invert. You cannot simply take the negative value for K. So that's a little different.